double check the connections. Okay, is there any questions before we move on to lectures? Any questions, guys? Okay. All right, let me set up the YouTube streaming so I can. Oops, what is going on here? Okay. All right. All right. Wait a second. I think there's some connections issues on my YouTube channel. Sorry about that. Okay, now I'm going to copy a link and send it to the group chat, and that's a link to my YouTube channel, to where all the YouTube the videos will be posted to. Okay. All right, check your group Zoom group chat, and that's a link for the future lecture videos. So another benefit of using this live stream, I think, at the end of each live stream, it will just automatically save the video on the channel, so you can revisit the video meantime as you want. Okay, are you guys on there? Oh, you can just leave the Zoom meeting on. Since you can only talk through Zoom on meeting, so leave it on can give you access to like ask questions. Oops. Oh, the echo is going crazy. All right. Okay, I'm gonna mute everyone. Okay. All right. Hopefully everybody can see my screen. Okay. All right. Everyone can see my screen, right? If you can't see my live stream, and just leave a comment there, or give me a thumbs up, and so I know everybody's there. All right. I think we're live now. Okay. Yep, we're live now, and everything should be good. Can you guys hear me as well? Okay, if you can hear me, so let's get started. So last time we talked about the data processing system, a general data processing system, and you will have a analog input, and that can be a voltage signal or current signal, and that signal goes through a filter to get rid of the noise, and then it will give you a much smoother analog signal. But beforehand, there's be signals, noise like that. And then the analog signal goes through ADC. What is ADC? Analog digital converter. So that will convert this continuous analog signal into a infinite number, binary number actually. So it will give you something, a sequence of numbers, binary numbers, from after ADC. Now after that, it goes into the computer for data processing and it give you out another sequence of binary numbers. Then this sequence of binary numbers, binary words, where it goes into DAC. What is DAC? It's a digital analog converter. And then after that, it will give you a staircased analog signal. So it's try to simulate what the analog signal looks like, but with that staircase shape. And then this kind of like a simulated signal, analog signal, goes through the filter, give you a much smoother analog output. So this is kind of the whole process of data processing. And last time we put a little bit more focus on the DAC, which is DAC. We mentioned different types of DACs, for example, resistor string DACs. And what other DACs you remember? Mentioned many different types of DACs, and just want to give you a 20 minutes pause to remind yourself what other DACs you have. And remember that's the first one is called resistor string, and the second one is called linear combiner DAC. Then we give example on how to connect the chip when you have a unipolar setup, right? So today we're gonna move on to ADC, which is analog digital conversion. And the reason we introduce DAC first is because DAC it's simpler than ADC. ADC it's much complicated, and you will see that later. Instead of an ADC chip, it actually include a DAC module inside. So we're going to look at what is DAC and what's the different types of DAC and their pros and cons. Jump to here. Okay. All right. So let's look at the first type of DAC. Yep, the first type of DAC, and it's called counter or ramped ADC, analog digital converter. And just think, before we get into this, I want you to think about this. ADC should be the first interface, the first components kind of in between your input signal. What are those input signals? Those signals should come from the sensors in your project. So in your project, if you have a temperature sensor or force sensor, and it will sense all the information in the environment and convert that into a signal. That signal should go through the DAC. First, it will go through a filter maybe, then ADC. So because all the information you sense from the environment are digital information, you want to convert that into a digital information. So that's what A and D represents for. And instead of this counter ramp DAC, this is the simplest ADC, ADC you can find. So the analog sample input is on this side, and those are the signals. Either it can be voltage signal or current signal. Those analog signal go through a component, looks like a triangle. Remember what's this component is called? Can someone just comment on the chat to tell me what's the name of this components? Yeah, op-amp. Exactly. And yes, this is op-amp. But this op-amp has the application as a comparator. Yes, Bern, you're right. This is a comparator. So it has two ends and it compares the voltage at both ends all the time. And the output, it's either a high or low from this comparator. So if you don't remember, let's do a quick review on the comparator. All right, a comparator, it's a op-amp, and let's change the thickness. So at this op-amp, there's an inverting side and non-inverting side, and this is output. So in order to have a comparator, you need to connect the inverting side, the negative side, to your reference voltage, and you need to connect this positive side to the voltage input, and that's it. There's no feedbacks, and on output, this is V out. Of course, for op-amp, you need to have power supplies, plus VCC and negative power supply VCC. And the output characters of comparator is like this. So this, it's a V out. And on the horizontal axis, it's V in, that's the input. The output voltage will look like this. Okay, so the maximum output here, the value is plus VCC, and on the negative end, this maximum negative voltage output is negative VCC. So that tells you if your V in, that's input voltage, is greater than the reference voltage, REF, which means this input end voltage is greater than the reference voltage, greater than this inverting side, and you will have a positive saturation voltage, which is VCC. And you can manually give maybe 3 volts for this VCC, then you will get a 3 volt output when this V in is greater than the V reference. For the negative output, that's when you have V in smaller than your V reference. So when your input voltage, which is right here, smaller than this reference voltage, you will have a negative output, negative VCC. And we can manually set this negative VCC to 0 volt. Then that will make you have a 0 voltage output if your V in is smaller than V reference. And that's the case for this this ADC here. So this comparator compares the analog input signal with another signal as a reference signal, and will give you either a high or low signal at the output. And this high and low output goes into this gate. This guy here, it's a logic gate. Remember that? A logic gate. What's the name of that logic gate? Can someone tell me what's the name of that logic gate? Just type it on the chat. Yeah, it's an AND gate. That's right. So the AND gate, one end of the AND gate is connected to the sorry. the one end of this AND gate is connected to the output from this op-amp. Another end of the AND gate is connected to the clock signal, which is a pulse signal. And it will give you either low and a high, right? And then here, this block is called counter. Oops. And this counter, what this counter does is it counts the number, how many times this signal goes through this counter. And it counts from the low, from 0, all the way to a number that is larger than this input analog signal. So the counter will generate a sequence of binary numbers, and that sequence of binary numbers start from 000 if this is a 3-bit, and all the way to 111, right? And what we learn in the DAC is we can convert that 3-bit number into an analog voltage value, right? And for example, 11000 represents the smallest voltage output, that is 0 volt. And if we have a full range, full scale of 3 volt, and this 111 after this DAC will give you something a little bit smaller than 3 volt. And that value goes into this op-amp, this comparator, to compare with this analog signal. If that value is greater than that, and this whole thing will froze this digital sequence, and I use that as the value for the analog sample input. So this is actually very ingenious and the simplest idea to kind of record what is this analog signal. So it just, at each time step, it just counts from 0 all the way to the maximum, and until it hits a point that value is greater or equal to the analog signal, then it will record that signal. And so they will do this at each time step, at each sampling time step, until you get a record of all the analog signals. And so the point of this counter or ramp ADC is very simple, and the idea, the logic behind it is very simple. And however, it suffers low speed. Imagine, and you have to count every single time, you have to count from 0 all the way to whatever that input analog signal is. And so if we have the bit number n increases, and the number of count going to be very large, that means it takes longer time to count, right? If this is a 3-bit, 2 to the 3 is 8, it's not too bad, right? But if that is the bit number of bit is like 12, 14, or 20, and this number will be increasing exponentially. So that's the pros and cons of this counter ramp ADC. All right, if any questions, that's the simplest form of ADC. And if you don't have questions, don't have any question, give me a thumbs up on the chat so I know I can move on to the next type of ADC. Okay. All right, got some comments here. All right, let's move on to the next type of ADC. The next type of ADC is called SADC. It stands for Successive Approximation ADC. And just like the first ramp ADC, the analog sample input goes into a comparator here. Then another end of this comparator comes from a DAC, a DAC, a digital analog converter. And what is going on inside is a little bit different. It has a controls logic module, and it has the output register. So what this type of ADC is doing is it guesses what should be the value for the input analog signal. So every time if you have let's give this example. Let's just use red. We're good. If we have a signal, the analog signal start from 0 volt all the way to 3 volt. And what we learn in DAC is we can map the range between 0 volt to 3 volt into a sequence of digital numbers all the way from 000 all the way to 111, right? And each binary code represents a value of analog signal. Yeah, we did that last week. And so every single time whenever you have a new analog input, it would first compare that input. Let's see that input is X. It will compare the value of X with the middle number in between 000 and 111, that is 100, 100. So it will first compare this X with 100. If X is greater than 100, and then the guess process will move to the upper branch. And it will further compare this X value with 110. And if the X is greater than 110, it will move on to 111. If that is smaller than 110, it will move on to 101. So let's assume in this case the X is smaller than 110, so it will move on to this branch. And then it do another comparison between the X with 101. If X is greater than 101, they will move on to the upper branch 101. And if that is smaller than 101, that will move on to the lower branch. Now eventually you will end up with a sequence of binary number, and that is corresponding to the value of X just by guessing multiple times. So that's kind of the logic. By guessing, I think in this case, n times 3-bit, 1, 2, 3 times, yes. And so for this SA ADC, it is very fast, because if you compare that with a ramp ADC, you have to count the number all the way from 000 all the way to whatever that number is. This SA ADC is very fast because it only needs n clock cycles. That n is the bit of ADC. If we have 3-digit ADC, then you only need 3 clock cycles. And the cons is it has high complexity than the ramp ADC. The complexity comes from the logic, the control logic. Yeah, you have to use all the logic gates to represent what is going on here, and also you need a data register to convert everything to a digital output for the DAC. So it's more complex than the ramp ADC. All right, and next, we have another very popular ADC, which is called flash ADC. Just like the name suggested, it's very fast. And so the circuit of this flash ADC looks like this. It has bunch of resistors are connected in series, like on this end, and in between each resistors, and there is a branch goes into a comparator, and the other set of comparator is all connected with this analog signal voltage input, signal input. And so I want you to look at the left side first. So on the top here, we have VFS, that is the full scale voltage of this analog signal. Let's see if that is 3 volt. And on the bottom here, here's a ground. So do this thing look familiar to you? You have high voltage, low voltage, and a bunch of resistors in between, and you have some a wire come out from there. So can someone tell me what's the name of this circuit, of this application? Just type it out on the chat. Yeah, it is a voltage divider. You're right, Dennis. This is a voltage divider, right? So it divides the voltage into depends on how many bits we have. So it divides voltage depends on how many resistors we have. So it would be a small percent of this VFS at each comparator. Then, so what it's doing here is all of these comparators here are comparing the input signal, analog signal in real time and to the referenced voltage signal. And with the decoder to decode this M to N decoder and give you a 3-bit, it depends on how many bits you have. In this case, we have 3 bits, or give you a 3-bit digital output. And hopefully you see what it's doing here. So it's using comparator to compare just one analog signal with all the possible voltage signal, reference signal, and to see which one it matches with the current analog signal. So the advantage of this, I think our Zoom meeting time it's ended, so I guess a lot of you got kicked out by Zoom. Then you have to reconnect again on Zoom. So let's pause here to reconnect, so in case you need to ask questions on Zoom. Okay, let's get back to this flash ADC. And so if you look at this logic diagram of flash ADC, it requires, oops, the echo is going on here. Let me mute. All right, so this flash ADC will need 2 to the n minus 1 of comparators and needs 2 to the n resistors. Okay, let's back to here. So if our bit number is small, like for example 3, and it's not too bad, you only need 7 comparators and 8 resistors to get a decent flash ADC. However, if we have 8-bit, then that number increases to 250 comparators. If we have 16-bit, and you will need more than 65,000 comparators. So for the limitation of this flash ADC is, if you want to have like high precision of this ADC, you want more bits, that will significantly increase the complexity of the circuitry. And however, it just so fast, the speed is just very good for the flash ADC. I think for your project, you don't really need something very precise. So I think flash ADC would probably do the work and give you a very fast data conversion. Okay, and so far we talked about flash ADC and successive approximation ADC and the counter or ramp ADC. Three popular type ADCs. There are other different types of ADCs. Here you probably will see, like for example, dual or single slope integrating ADC, sigma delta ADC, pipeline ADC. And those are other types of ADCs. Probably will give you some trade-off between speed and accuracy, but we won't talk about that in this class. But let's look at the summary, the comparison between different types of ADC. So here I created a table. On this side we have different types of ADCs. We talked about ramp, SA, flash ADCs. We didn't mention so much about integrating ADC, but that's fine. Let's look at the speed between them. Like we said, this flash ADC is very responsive. It has a very high speed, and the time cost to convert data is only the time that you need for the clock time. And if we look at the SA ADC, the speed is median. The time needed to convert data is n times the time of clock. So n, that's a bit. The more bits you have, the longer time it needs to convert data. And the RAM ADC needs the longest time, the converting time, 2 to the n minus 1 times clock time. So it's pretty slow. The RAM ADC is pretty slow. However, RAM ADC has a median precision, and the complexity and the cost are median. And similarly for SA ADCs. But for flash ADC, it's not very accurate. It has a low precision, but it's quite complex and it has a higher cost. For integrating ADC, it has low speed but very high precision, and the complexity and cost are low. And the time needed is greater than 2 to the nth times clock time. Which is longer than the ramped ADC. And here is a chart to show how each different types of ADC are mapped in terms of frequency, Fs, and bits. So the frequency Fs here means the sampling ADC, how fast the ADC can sample and record data. It's all the way from very small 0 to 1 gigahertz. And the bits, it's just the bits you have for your ADC. Start from 4 to 24. So let's look at the lower end of bits. Your flash ADC only have the configuration between like 4 to 8 bits, but it could give you a very high sampling frequency. The next we have pipelined ADC, we didn't cover that, but that's one type of ADC, and you can use a little bit higher bit numbers, but it gives you a smaller and slower sampling rate. And if we go to even slower sampling rate, lower sampling frequencies, and we have this successive approximation ADC that can varies from 4-bit all the way to 20-bit. So it has wide range, but it has quite low sampling frequency. And on this, it's the sigma delta ADC. It's kind of like in between. On the top here, we have a ramp and integrating ADC. It's pretty slow, but it's very accurate. And because the sampling frequency is less than 100 kHz, but it can use a very many bits and give you a high precision. All right, so this will conclude different types of ADC that hopefully help you to choose the analog digital converter for your project or for any future application. Oops. And any questions before we move on? So far, we covered DAC, now this is ADC, and you should have a general idea how analog and digital data are connected for the mechatronic systems. All right, if you don't have any questions, give me a thumbs up so I know everybody is on the same page. And if you have questions, feel free to just use Zoom to ask your questions. Okay. Okay. I think we're pretty good here. So if you have any type of questions, and the video will be saved as a video on this channel, and you can always come back to revisit the material. Yeah, and by the way, subscribe my channel to make me a famous YouTuber. I'm just joking. We only have 16 students, so. All right. So I think last time Carl asked me what is a filter and how to build a filter, right? So I think I put some materials to show you what do we mean about filter, because at the very beginning we mentioned that the data will go through a filter before it goes in or goes out. So now let's talk about very widely used low-pass filter. So low-pass filter, just like the name is suggesting, low pass, it allows low frequency signal to pass. Oops. Wait a second, let me double check my live stream. Okay, I think we're good. All right. So it only allows the low frequency to pass. Low frequency to pass. And it reduces the amplitude of high frequency signals. So what does that mean is, here's a plot. On this axis, it's the amplitude of a signal. And on this direction, it's frequency of a signal. So you can have a signal that has a wide range of frequency, all the way start from low to high, all the way to 20k hertz. Let's add a units here. And however, in some of the especially in data conversion, we don't really need the high frequency signal. The reason being, most of the high frequency signals are noise come from the environment. So we want to get rid of those high frequency noise. That's how this low pass filter comes to play. It cut the high frequency signals, only leave the low frequency signals for your data conversion purpose. And so what it does is it adjusts the amplitude of the signal, like here from 0 to 1, 1 being 1% of the amplitude. So before this, FC represents a cutoff voltage, cut off frequency. And if the frequency is smaller than cutoff frequency, that's here, and it keeps the 100% amplitude of the signal. So it just record whatever is there, doesn't change anything. However, if the frequency is larger than FC, the amplitude of the signal will be decreased, will be cut. So you see this here has a steep decreasing of amplitude all the way to 0, which means if your frequency is larger than FC, much larger than FC, it gives you 0 as the output. So that's how it kind of like stop all the high frequency signals. And also has a name called anti-aliasing filters in data conversion. And this type of low pass frequency has a very wide application, and it's been used to conditioning DC power and used for data acquisition. And if you are a audio guy, and a lot of projects you do will require low pass frequency, low pass filter. And let's look at an example, how to build your own low pass filter. So in the low pass filter circuit actually looks something very similar to voltage divider. And however, when we talk about data conversion, and we usually have AC signal of AC voltage source instead of DC signal. And you have R1, R2, have a output here. And so R1, R2 serves as a voltage divider, divide the voltage. And here, if you use the oscillator, and you will get a plot of what's the change of voltage at this output, V out. And the low pass filter looks very similar to this voltage divider. It just simply replaces R2 with a capacitor like this. So it gets rid of I2, R2, this is R1, and it adds a capacitor here. You still have the V in and V out, and that's the most basic low pass filter you can build. However, you may have the question, how I decide the value for R and R1 and C? That really depends on the particular application you have. We're going to mention that later. But remember, if you want to have a low pass filter, or you heard about that word, that's probably a RC low pass filter with a capacitor and a resistor. And Since here we're talking about AC signals, so I want to um, just clarify some of the concepts here. So you probably heard impedance a lot, and we usually use Z to represent impedance. And impedance, it's just a AC version of resistance. So there's no difference. It's just an AC version of resistance R. And so that you can still apply Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law to your circuit. Just treat that as a resistance. And we usually use Z. If you add R, that's just resistance. If you have Z subscript C, that represents the impedance from the capacitor. So ZC it equals 1 over J omega C. And here omega is a frequency and C is a capacitor, capacitance of the capacitor. And J here, J equals square root -1. Okay. All right. So that's some of the just what is impedance. And let's go back to this low pass filter circuit. And like I mentioned, you can still use other laws to this circuit. So you can first apply Kirchhoff's voltage law. So V in can be written as IR, current times R, plus I times the impedance come from the capacitor, which is here. That term is ZC. Yep. And then we can use Ohm's law to rewrite VR equals just IR, and VC, the voltage drop. VC, voltage drop here on both ends of the capacitor equals I times ZC, which is the V out, right? And then we can rewrite this V in equation to V in equals IR plus V out. And here what we're trying to do is we try to get rid of this I. We don't really need current in this analysis. We want something in terms of frequency. So I want to substitute this I in terms of V out times J omega C. Where I get that? I get that from here. So you pretty much throw everything else on the other side of the equation and just keep I on one side of the equation. Then you get this. Then you have this expression for current. Substitute this current into this expression, and you end up with expression of V in equals V out J omega CR plus V out. And we can rearrange this to get a relation between V out and V in. And then there you go. You get V out versus V in equals 1 over 1 plus J omega RC. And this is a transform function for this low pass filter. And I want you to look at if your omega goes to very large number, what would that do to this equation? Imagine your omega is very large, this whole term where it goes to 0, right? And if this is 0, and that means V out versus V in equals 0. And your V out is 0. That means if you have a large frequency, your output is 0, right? That's what we're trying to do, to get rid of all the signal has high frequency. And now let's look at what if our frequency is very low, omega goes to 0. And this whole thing, J omega RC goes to 0, you end up with 1. What that means is V out versus V in equals 1. So it copies whatever is the input. That's what this diagram is for. That's what it means for this diagram, this plot here. When the frequency is low, it keeps the amplitude of 1 for all the signal. It just copies all the signal. If your frequency goes very high, it reduces the signal to 0. Now you know what is a low pass filter. Okay, let's move on. Okay, now let's do a quick practice. Build your own anti-aliasing filter, so which is also you can call build your own low pass filter. And if you remember, during last week we mentioned the rule of sampling, that is the Nyquist-Shannon theorem. So the sampling frequency fs need to be larger than 2 times of the maximum frequency of the data of the analog signal. But in real world, you better choose that greater, maybe 10 times or 20 times to keep the performance. Okay, so we know that, and we want to choose, by the way, the cutoff frequency Fc equals 1 over 2 pi Rc. Fc, it's the frequency right here. That's where you start to filter out the the transition point. You start to filter out all the high frequency signal. And if now we have a sample frequency, let's look at this example practice. Sample frequency equals 10,000 hertz. All you can see equals 10,000 samples per second. So this way it's easier to understand, which means this ADC can sample 10,000 samples each second. So it's very quite fast. And the maximum of the analog signal you're trying to sampling would be just fs versus 2 equals 5,000 hertz. That's just come from this, the rule, the theorem. The sampling frequency has to be 2 times larger than the maximum frequency of your analog signal. Now we know the maximum frequency should be here, and therefore if you want to do the filtering, you want to filter out all the frequency that is greater than 5,000 hertz. However, if we go back here, the low pass filter will kind of have this decreasing zone, so you need to give a buffer or margin for that the frequency you want to filter out. That's why we want to choose a little bit smaller frequency for your design. We want to choose the cutoff frequency equals around 4,000 hertz, which is slightly smaller than this maximum frequency there. Then this cutoff frequency from the formula should equals 1 over 2 pi Rc. And if you have, just for example, if you have a resistor that is 1,000 ohm that is available to you to build this low pass RC circuit, which is right here. Let's say this R equals 1,000 ohm, which is 1 kilo ohm. And you should be able to decide what is the capacitor you need to use for this low pass filter in order to filter out all the frequency that is larger than 5,000 hertz. And that will be just a very simple calculation, right? To calculate capacitance C, and C equals 1 over 2 pi R Fc. just from here. We're trying to solve this C here. And you will find out the capacitance you need to use is around 4 picofarads, and which is around 0.004 microfarads. There you go. If you have a resistor that is 1 kilo ohm, you have a 4 picofarads capacitor, you are able to build a low pass filter to filter out all the frequency that is greater than 5,000 hertz. And this is just example to show you how to build your simple low pass frequency based on the maximum frequency and the sample frequency you have. So for the particular application in your project, you would need to check the data sheet of your ADC and to find out what is this FS is. Then you will need to analyze the signal you're trying to sampling. It can either be the force or temperature or whatever, and to find out what's the maximum frequency of that signal. Then you can do some simple calculation and to find out the resistance and capacitor you need to use for your low pass filter. All right, hopefully that give you a little bit knowledge on what is a low pass filter. Okay, any questions? Yeah, you can either ask question on the chat or just use Zoom to unmute yourself to ask questions. Sorry, is someone asking questions? Okay, if you have any questions, just type on the chat maybe. So I'll mute all of you, but I heard some background talking conversations going on. I'm not sure who is talking. But yeah, this will be just everything about data conversion. And we did ADC, DAC, and low pass filter. And those are the important components for data acquisition, data conversions. All right, if you don't have any questions, give me a thumbs up. Okay, we have about 15 minutes left. All right. Okay, I would probably after upload the notes on Moodle. Yeah, you will have the video access through the YouTube channel, but I will upload this PDF version of the notes to Moodle, so you are free to take a look at the notes anytime you want. And now let's get started on another very widely used components. It's called 5-5 timer. I think we have a little bit of time to get started on this so we can finish this up next time. So probably you already heard 5-5 timer It's a widely used component to perform time tasks. What do I mean time tasks? So anything that relate to time. For example, during your project proposal, I heard a lot of you said you want to light up an LED or something uh, after how many few seconds, few minutes, or few hours to as an indicator for something in your project. So if you are trying to get this type of application done, F 5 timers is gonna be a very useful components for your design. So it can be used for applications such as bounce-free switches. We mentioned that, right? We watched the video on bounce-free switches. Do you remember switch trigger? That's something I think related to that. And also it's used for frequency dividers, voltage controlled oscillators, and pulse generator and LED flashes. I think those two are very useful. Pulse generator and LED flashes. The bounce-free switches are also very useful in terms of this 5-5 timer. So 5-5 timer is usually comes with IC chip. Usually has probably 8 legs, 8 pins, and but it can do a lot of things. Oops. And let's take a look inside of this 5-5 timer. And the 5-5 timer, it's also called time machine. Yeah, it deals with all the time related tasks. And inside of this, the IC chip probably like a square shape, but inside of the chip, and there's so many things going on. First, it has 3 resistors on this side, and on top is connected to VCC, which is power supply. On the bottom here is connected to VSS, which is ground. Well, here is it again, voltage divider, right? And also here we have 2 comparators. One is called threshold comparator, another one is called trigger comparator. We did a review on comparator before we start the ADC, so I think you guys are good there. And on here, this block here, we have a flip-flop. It's not a flip-flop on your feet. It's electronic components. It's called flip-flop. And okay, and a quiz here. We have another components right here. I want you to type on the group chat. Tell me what's the name of this component. BGT, yes, bipolar transistors. It's a transistor. So those are the main components inside of this 5-5 timer. And it has few pins. It has a output reset VCC, control threshold, which is an input voltage input signal, and a trigger input signal, and discharge pin and the ground pin. Okay, let's see if we have 10 minutes left. Let's see if we have time to go over what is flip-flop. Okay, let's leave flip-flop next time. So let's get started on this so we can keep continuing on 5-5 timer next time. So first thing I want to get on is this voltage divider. At this point will give you a voltage output of 2/3 of VCC because it's a voltage divider, and at this point it will give you 1/3 of VCC. Let's write this out, VCC. All right, and at this end, this will be just V equals 0, 0 times VCC. And then the comparator, to compare the VCC, the different fractions of VCC with the input signal, which is called control threshold voltage and the trigger voltage input. And the output from the capacitors and the comparators, hopefully you still remember that, is either a high or low, right? Either is 1 or 0. 1 or 0. It's a logic output, high or low. Those high or low information what goes into this flip-flop. Flip-flop, it's a sequential logic component to do logic calculation. And I want you to recall what we learned for logic, all the logic gates. Remember how many logic gates we learned? We learned tons of logic gates. Let's fast forward a little bit. Okay. Remember that? Let's review this. The logic, the first logic gate that looks like that, and with a circle here, and that is called NOR gate, right? And it's pretty much a NOR gate, an OR gate, but plus an inverse. So it inverts everything from an OR gate. And this, it's a non-AND gate, an AND gate. So its AND gate has a inverse. So what's the name of this one? Without the circle, of course, is OR gate. This one here, without the circle, it's called AND gate. And one more thing, test, what is this called? Can anybody tell me what's the name of this logic gate? By the way, don't confuse this with comparator. This has nothing to do with comparator. They look pretty similar. They all have the triangle shape. But this is an inverter, or you can call it NOT gate. So it inverts everything. If you have 0, it will give you 1. If you have 1, it gives you 0. Okay. And the reason we want to review on this because inside of flip-flop, it has either NOR gate or NAND gate to give you the performance, to give you certain function output. And we're gonna look more in details on flip-flop next time. All right, we have 6 minutes left. I would like to answer any questions, or if you have any suggestions on how should we do this online classes, please leave a comments below. Otherwise, you can subscribe my channel and hit the thumbs up button, I guess. And that's how do other YouTubers usually see when they try to end their video. Stay tuned. Is that right? Okay, so that's today's lecture, and feel free. I will leave the Zoom meeting on so you can keep asking questions, and but I will close this live stream. All right, smash that like button. Yes, that's right. Okay, see you guys on Thursday.